Hi, everybody. I'm Erin Walker. I'm faculty at the University of Pittsburgh in the School of Computing and Information in the Learning, Research, and Development Center. And I'm going to talk to you today about my lab's efforts in the intelligent modeling and support of reading comprehension processes. This quote is from the National Education Technology Plan in 2010, so it's a little old at this point, but I think it's still highly relevant today. And it says the challenge for our education system is to leverage the learning sciences and modern technology to create relevant, engaging, and personalized learning experiences for all learners. So given a learner's prior knowledge, given their motivation, given their experiences in a particular domain up to this point, how do we provide them with an experience that is tailored specifically to what they need? And a lot of the research on artificial intelligence and educational technologies right now are focusing on this exact question. And when I think of the role of technology in providing these kinds of personalized learning experiences, I think of it along three different dimensions. So first, technology can create novel learning experiences for the learner. So if the learner puts on a VR headset, they might be transported to ancient Rome and all of a sudden have a much richer appreciation for history than if they were reading about ancient Rome in a textbook. And then as the learner interacts with a learning environment, we can collect data about how they're interacting, what their strategies are, and what works and what doesn't for their learning. And the way the learning environment is designed is going to inform the kind of data that we can collect. And then based on the data we collect, we can adapt the experience to the learner in real time. And this isn't exactly a new framing. So intelligent tutoring systems have been doing this kind of thing for several years now. Intelligent tutoring systems model how learners solve problems and then provide them with adaptive support. And they've been very successful in well-defined domains like math and science, where there's an obvious right or wrong answer, and there's a clear path to that answer. Some strategies that intelligent tutoring system designers use are to make a student's thinking visible by providing them with scaffolding like tables or text boxes to fill out that represent sub-goals of the problem. And then based on how students are interacting with the system, modeling their correct knowledge, their misconceptions, and then giving them immediate feedback that's individualized specifically to what they understand and what they don't understand. On the other hand, reading comprehension is a foundational skill for understanding both narrative text and informational text, but it's more complex to support by something like an intelligent tutoring system because it's not always obvious how to understand reading comprehension strategies and then in the moment provide students with the kind of support that they need to engage in more productive strategies. And there is a growing body of work on intelligent tutoring systems in this area. So our work builds on this body of work to examine two different ways of collecting data that allow us to make inferences about what's occurring during reading comprehension and author support. And so I'm going to tell you about two different projects that offer these two different methodologies. The first project is MindDot, which is a content mapping application for high school and college students that attempts to support reading comprehension as students study informational text. And the second one is Embrace, which is an intelligent tutoring system for English language learning targeted towards primary school learners. So the first project I'm going to introduce for you is MindDot, where we're examining how we can use a concept mapping interface to understand and support reading comprehension strategies. The core of MindDot is the concept map. So in a concept map, you have nodes representing key concepts, and then you have links between those concepts representing the relationships between nodes. And concept maps are ways of organizing a body of knowledge. As students construct concept maps while they're reading text, they tend to understand the text better and recall more about the domain. And this is particularly true when they're engaging in comparative strategies while they're reading the text. Constructing a concept map requires students to identify key concepts and then the relationships between those concepts. So the act of making comparisons between concepts to identify their relationships is highly beneficial for learning. Unfortunately, concept mapping tasks also have drawbacks. So it's highly complex, it can be time consuming, and therefore it can be demotivating for students if they find themselves struggling to construct a concept map based on a text. One way of overcoming some of these limitations and supporting students in concept mapping is through hyperlink navigation, where nodes in the concept map are hyperlinked to the content that students are reading or trying to process. Previous systems that have used hyperlink navigation using ready-made maps that have been given to students have yielded mixed results. And part of the hypothesis there is that it can be difficult to process a map that you didn't make and then use it for navigation. But we have found in our previous work that by allowing students to hyperlink their nodes to content in a text as they're creating their own maps, they do improve their comparative strategies or their ways that they're making comparisons between concepts in the text. Another often used strategies for supporting students in constructing concept maps are expert templates, where students build maps from a template. This can be faster than constructing a map all by yourself, and it gives students some idea of the expectations for what kinds of concepts should be in the map. But again, it can be difficult for students to process a template that they didn't make. So in our work, our goals were to build a system that combines the two forms of support during concept map construction, and then analyze the way that students use the system to reveal how they engage in comparative strategies during concept mapping. So the notion here is through this design of a learning environment where we have hyperlink navigation and we have template-based support, we can get some insights into how students are engaging in these comparative reading comprehension strategies that we wouldn't be able to get if students weren't interacting with these scaffolds as they were constructing the concept maps. Our system is called MindDot. It runs on an iPad, and it has this integrated text and concept map view where you have the text on the left and the concept map on the right. And we have loaded a chapter on biodiversity into the app. MindDot facilitates easy concept map construction. So concept nodes are created from the text by highlighting a word or set of words in the text, and then you can create a concept from that. Or they can be added separately if you don't want to directly take the words from the text. And then there's hyperlink navigation as part of the system, so you can click on a concept to go to the page where that concept was created. And when you get to that page, the concepts for a given page are highlighted. So you can see that point source, non-point sources, and water pollution are highlighted in the concept map and also in the text. And when using MindDot, we also provide students with an incomplete expert template that includes 8 key concept nodes spanning 7 different pages of the text out of 20. And the expert template comes pre-hyperlinked to the text. So we had 3 different hypotheses about this learning environment: that the hyperlink and template support together would improve domain learning, that the hyperlink and template support would facilitate comparative strategies, so students in making comparisons between concepts. And again, that's a subset of these reading comprehension strategies that we're hoping to facilitate. And then that the student use of comparative strategies predicts their learning outcomes. In our study, we had 59 college students, and they engaged in 30 minutes of concept mapping with 10 minutes of pre-tests beforehand and a 10-minute post-test afterwards. And we had 4 conditions. So one condition combined the hyperlink and template support. One condition was hyperlink alone. One condition was templates alone. And then the other condition, there was no hyperlink and no templates. And then we had several measures of comparative strategies that we had devised using a previous study with the system. So first, back navigations, or the number of times students navigate back to a previous page. And the idea here is that if students are navigating back to a previous page, they're probably going back to make a comparison between a concept on that page and a concept on the page they were on previously. The second one is crosslinks. So the number of linked concept nodes from different pages. So for example, A and C represent the link between A and C represents a crosslink because they were created on different pages, whereas the link between A and B doesn't represent a crosslink. And then context switches, or the number of times the learner switches their interaction between the textbook and concept map view. So obviously these 3 metrics aren't foolproof indicators of comparative strategies, but we were hoping they were proxies for that construct. They're the kinds of behaviors that students would engage in most likely if they were making comparisons between concepts as they were drawing their concept maps. We found that all students learned, but the hyperlink feature significantly improved learning compared to the template-only condition and the no template conditions. The template feature didn't appear to have a significant effect on learning, and there was no interaction effect. So this is some evidence that hyperlink support is effective for improving learning. We also found that hyperlinks improve comparative strategies. So as total actions increase hyperlink support, led to more back navigation than more context switches. The graph shows back navigations as an illustration. And again, there was no significant effect of template support on comparative strategies, although template support did have a marginal effect on crosslinks. And then we also found that comparative strategies predict learning. So the 3 comparative strategy metrics were significantly correlated with the post-test, controlling for the pre-test. And this is exciting because it does show that by examining student interactions with the system in this way, we're able to determine if they're engaging in these productive reading comprehension strategies that then will lead to greater mastery of the domain concepts. We then moved to looking more closely at student patterns of interaction with the system, and I'm going to talk about one way that we did that, which was using a sequence diagram. The sequence diagram decomposes concept mapping into the sequences of key actions that students engage in prior to adding a node. And in particular, we were interested in looking at 4 actions. Read, where students are moving forward in the book. Compare, where students move backwards in the textbook, in theory with the goal of making a comparison. Linking, where students make a link between concepts on the same page, and then cross-linking, where the students make a link between concepts on a different page. And so if this is a string of student actions over time, we extract the sequences as follows. We take all the actions up to the first time students add a concept, and that's one sequence: read, compare, then link. And then we take all the actions up to the second time students add a concept, and that's a different sequence: read, read, link, read. And then aggregate all the sequences together into this visualization that then reveals commonalities across different groups of students. So for example, that visualization on the left is an aggregation of the sequence diagrams of all the students who got a perfect score on the post-test. And we can compare that to the diagram on the right, which is an aggregation of all the sequences from students who had negative learning gains. And we can see that on the left, students took more actions prior to adding a node, and they moved back and forth quite a bit between things like compare and link, compare and cross-link, read and link. They moved back and forth quite a bit between different types of actions. Whereas students who had negative learning gains took fewer steps before adding a node. They had fewer of these horizontal switches back and forth. And then using these patterns that we extracted from visualizations like the sequence diagrams, we could identify patterns that then can be used as part of a model of good concept mapping and bad concept mapping, and then input to an intelligent feedback system. So for example, that read, read, read pattern at the top, where learners consecutively read more than 3 pages, is an example of limited horizontal switches that we saw in the low learning gain students. And so we can operationalize that as this pattern and then respond to that if it occurs in the system. And we can identify positive patterns too, like creating a crosslink. So the first crosslink students create, we can reinforce that with positive feedback. And in fact, we did build an intelligent feedback tutor that gets the sequence of student actions prior to adding a node, extracts the relevant patterns from those actions, compares the student concept map to an expert concept map, and then provides the students with feedback based on the pattern and the comparison between the student map and the expert map. So an example of what this looks like is first a process-based message. Hey, I noticed that you just read 3 pages. Anything interesting you would like to add to your map? And then if they click show me some, a content-based message, sample nodes from an expert concept map that they might want to add to their own maps. And so we designed this system mind up to scaffold content mapping through hyperlinks and templates. We did find that the hyperlink feature had positive effects on comparative strategies and learning gains, while on the other hand, we had little evidence that the template feature had a positive effect on student learning or on comparative strategies. But then we also used the data that we collected from student use of these scaffolds and use of the system to design a tutoring system that can respond to positive and negative student behaviors. And so here in this mapping of how technology can support personalized learning, we have this concept mapping interface, including hyperlinks and templates, that allows us to collect very specific data on student comparative strategies and behavioral patterns, which then allows us to adapt. We did implement this tutoring system and evaluate its effectiveness, and that work is going to be presented at CHI 2021. So I'm going to move on to the second project now, which takes a slightly different tactic by looking at what students don't do, or the pauses between their actions, to get a better understanding of student reading comprehension. So our question here was, how can we use response times to understand more about students' reading comprehension? And the motivation here was that in a lot of educational data mining, response time is often used as a key predictor of student performance and cognitive states. But previous work often uses response time as a whole, so the time between two actions in log data. And then its surrounding context, like whether students made an error previously or whether they took a correct step previously, to explain cognitive steps that students go through. Are they gaming? Are they responding to an error? But it's much rarer to see people exploring the time spent on cognitive states within a response time or trying to decompose this response time into different cognitive states. So in this work, we propose a model that uses the time spent on different cognitive states as subcategories of response time to give better predictions of student performance, with the ultimate goal of then adaptively responding in real time to these cognitive states. The cognitive states that we were interested in were productive thinking. So examples of productive thinking might be reflection or self-explanation. Gaming the system, where students just guess, they ask for a hint, and then input that hint as their response. They're not really engaged in learning with this system. And then unproductive thinking, like wheel spinning or mind wandering, the kinds of activities where students might be distracted or they may just be stuck on a problem. And our platform for this was a intelligent app that we designed called Embrace, where students demonstrate a story by moving images as they read. So a student might read, Sophia grabbed the bowl with red chilies and gave it to her mother to grind them, and then move Sophia to the bowl of red chilies. And the advantage behind this is it helps the students to simulate cognitively what's happening in the story, and therefore they can understand the story better. So this is based on a theory of embodied cognition. In Embrace, students can also ask for help to hear how specific words are pronounced. And then student manipulations are compared to encoded solutions, and feedback is given to the student if the manipulation is incorrect. So as an aside, Embrace is the foundation for a full-fledged intelligent tutoring system where we use this reification of cognitive simulation, the children moving the images in the environment, to identify particular skills that students are engaging in, like if they know particular vocabulary words, if they've mastered medium level syntax, complex syntax, to detect particular kinds of errors, syntax errors or vocabulary errors based on the kinds of movements they do, and then to give them both targeted feedback and adaptive problem selection and vocabulary practice. So we've developed a full intelligent tutoring system around this embodied cognition scaffolding in much of a similar way that we developed an intelligent tutoring system surrounding the concept mapping scaffolding in the previous project. But what I actually want to talk about with this project is what we did with the controlled version of Embrace, which does not have the simulation or feedback features, and where student actions are restricted to reading a sentence, requesting help, and pressing next to move to the next sentence. Because we thought that we could actually learn a lot about reading comprehension based on the response time of a student or the time a student spends on a sentence before pressing next. So our question here was, what information do we have about what cognitive state students are in during reading comprehension without having any of that scaffolding that allows us to get a different lens on the student's state. We drew on 2 data sets for this experiment, but I'm going to only talk about one data set in the interest of time. That data set had 21 children who were native Spanish speakers who read 7 storybooks, and there were 716 unique student chapter pairs, so a particular student reading a particular chapter. And we measured the students' decoding ability in English, their comprehension through multiple choice questions, the chapter text difficulty, and then their frequency of help requests and frequency of gaming the system. And we'll talk a little bit more about that in a bit. So our goal here was to decompose response time into different cognitive states. And the 3 states that we were interested in were gaming, reading, and thinking. So we started off by identifying the time spent gaming, and then we identified the time spent reading, and then we broke thinking into productive thinking and unproductive thinking and attempted to identify the time spent in a productive thinking state. To identify the time spent gaming, the next button was disabled for 1 to 3 seconds based on the length of the sentence. And gaming students tend to press on the next button quite a bit, even when it was disabled frequently. So the time spent in gaming was the time spent between loading a new sentence and the last time the next button was pressed when it was disabled. We next identified the student time spent reading by starting with reading rate estimates based on a student grade, and then mapping that to a particular interval and letting our reading rate estimate be determined by both a student's decoding ability and the text difficulty. Then the reading time was the word count times 60 seconds divided by the reading rate per second. The final part of the response time we considered the thinking time. And we then used a data-driven method for distinguishing between productive time spent on a task and unproductive time spent on a task. So what we did was conduct a piecewise linear regression with student performance as an outcome and average thinking time as the predictor. And we did this at the student level. So for a given student, their regression using average thinking time to predict the correct answer proportion, and at the chapter level. And you can see the regressions make this triangle shape where their score goes up, goes up, goes up, goes up, and then they reach a particular thinking time, and then their score starts to go down. So we define that as the threshold between productive thinking and unproductive thinking. And essentially, we learned 2 regression equations to estimate lambda student and lambda chapter, imagining that student decoding ability would be a factor in predicting this threshold for the student, and the difficulty of the chapter would be a factor predicting this threshold for the chapter, and then combine the 2 equations into a single regression equation that for a given student and for a given chapter yields that threshold between productive and unproductive thinking time. And then if the thinking time that the student actually engaged in was greater than that threshold, their productive thinking time went up to that breakpoint, and then the unproductive thinking time was the total thinking time minus that threshold breakpoint. If their total thinking time was less than that threshold, then the productive thinking time related to the thinking time, and unproductive thinking time was set to 0. We then ran 3 different models. A decomposed response time model as a linear regression where we had features like the frequency of gaming, the frequency of help requests, the chapter difficulty, the student recording score, and then these decomposed response time variables. So time spent on reading, time spent on gaming, time spent on productive thinking, and time spent on unproductive thinking, against 2 baselines, a linear regression model and a piecewise regression model that did not have those decomposed response times, but only the response time as a whole. Our results found that for the first data set with the native Spanish speakers, the decomposed response time performed better than baseline 1 and baseline 2. So having those decomposed response time variables provided a better prediction of reading comprehension. So to summarize, we decomposed response time to account for different cognitive states: productive thinking time, unproductive thinking time, and time spent on gaming. And then we showed that the time spent on different states in a response time separately rather than response time as a whole gives a better prediction of student performance. So we can actually understand a lot about whether a student is engaging in productive reading comprehension just based on their response times to a problem. So our future work here is to scaffold productive thinking by adapting the time spent in productive and unproductive states in real time, so we can close that loop and build an intelligent system that actually responds to this real-time estimation of whether students are being productive or unproductive. So to summarize here, for this particular part of Embrace that I presented, we're looking at time spent on each interface element within the environment, and then we're estimating what cognitive state students were in between log events, and we have the potential to adapt based on that. So it's a very different approach than the previous approach where we're using student interactions with our scaffolding to figure out if they were engaging in productive comparative strategies. So in the presentation that I just gave you, we examined 2 different ways of collecting data that allow us to make inferences about what is occurring during reading comprehension and offer support. And thank you very much. I look forward to seeing